So we're going to kind of do here at the end of the course, a quick introduction to vectors a little bit. So some of you have already had vectors in physics, and what we're going to be looking at here is a little different. This is not going to be formula-driven. Physics vector operations are more formula-driven. What I want you to do here is be intuitive about vectors. What is a vector, and how can we do operations on a vector, and what are the applications of it? So a few skills that are important are kind of outlined in these review problems here. So how would we go about finding the values of x and y in problem number 1?
Find the x and then find the y.
How would you find x?
Go into the
Do what?
well, that angle
Crickets.
is 60.
The angle in the triangle is 60, but we could use 120 if we wanted to, because the reference angles are going to be the same, right? So x is equal to
That's the 90.
x is equal to r cosine of theta.
Wait, why?
Is that like the formula?
It's equal to r cosine theta. This goes back to polar form. The radius times remember the first component of polar form is the x coordinate, the second is the y coordinate. So if I were to write this formula, if I were to write this number in polar form, based on just what we did, what would it be? 15 times what? Cosine of 120 degrees plus I times the sine of 120 degrees. And if I wanted to put this into rectangular form, what would I do? Multiply this times the cosine of 120. Right? Cosine of 120 is negative 1/2. Right? So 15 times negative 1/2 is negative 7.5. And you could do this on your calculator. Negative 7.5. And then 15 times the sine of 120 degrees is 15 times the square root of 3 over 2. Which I don't know what that is. 15 times the square root of 3 over 2. In decimal form would be something else, but that's going to be 15 times the square root of 3 over 2.
Does the I go away?
Yeah, if we're writing it, if we're just finding the values of x and y, the I can go away. Right? So we're kind of jumping here. What I kind of want you to see is that we're jumping between the complex plane and the regular plane, polar form and rectangular form and coordinate form. I want you to see the connection of all of those things, because that's the stuff we've been dealing with in the last unit, and it all ties in together with vectors. All right, so what we have here, we're talking about a vector that's heading at 120 degrees with a force of 15. Now, we don't know if that's 15 pounds. We don't know if that's 15 miles per hour. We don't know that about it, but we could see this as a vector with a force of 15, a magnitude of 15, and a direction of 120 degrees. And then we could put it into rectangular form or a point form, coordinate form here. This is coordinate form of this thing, because that's the x and y coordinates of it. All right? So is everybody clear on how to do that? Now, if you wanted to go back even a little further without using polar form or any type of complex stuff, we could just take this triangle, and somebody pointed out immediately that this was 60 degrees, right? And this is 15. That means this is 30 degrees. And this is the short leg, which is 15 divided by 2. And this is the long leg, which is the short leg times the square root of 3. Okay, so we could use just special triangles, and it's what I want you to see is how all of this kind of comes crashing together. Okay, this is negative 15 over 2, and the other one is 15 square roots of 3 over 2. This was way faster to do it this way using the special triangles, but what if the angle was 105 degrees? Then you have to know the relationship between the other things, right? Or we're dealing with 35 degrees, which you're going to see in this final problem. All right, number two. Number two is a triangle problem. So for number two, solve, not a triangle problem, it's a calculator problem. Solve for theta in degrees. How would you do that? You're going to get out your calculators, and you're going to do the inverse sine of 3 divided by the square root of 11. Incidentally, whose calculator is this? It's been up here for like 3 days.
It's like Claire's, I think.
I think it is Claire's, you're right.
She's on here. Do we put this in degree mode or radian mode?
All right, it says in degrees, so
Oh,
you'll
okay.
want it to be in
I
degree
didn't see
mode.
that.
No, that's okay. And that's the question to ask, and I'm glad you asked it. The answer is there for us, and it absolutely needs to be. Inverse sine of 3 divided by the square root of 11. What do we get? 64.76 degrees. All right? Pretty simple.
Is this just a review?
This is just a review of some concepts, some ideas, some thinking that we're going to need for vector operations.
Okay, so you just
And then number 3, and this, Emma, this is an example of where we're headed. It says a naval ship leaves Port Norfolk and averaged 43 knots, that's nautical miles per hour. A nautical mile per hour is a little more than a regular mile per hour. I'm not real sure why, I've never done that research, but it's a nautical mile per hour. So I don't know, maybe this is about 50 miles per hour. This is a very, very fast ship, incidentally.
Hi. You got a fast.
Have any of you ever been 50 miles per hour on the water?
About 40.
It's fast. It's fast,
If
right?
you fly.
It is fun. All right.
You can't wear a
So
hat.
just you got a picture here. This is a naval ship. This thing is the size of all of our houses combined, and it's going that fast. A lot of power. It's pretty impressive.
It's terrifying.
But it's traveling for three hours on a bearing of 35 degrees. And then it switches course and travels for 4 hours on a course of 120 degrees. What is the boat's final bearing and distance from Port Norfolk after 70 hours?
So that'd be like the R.
That's it. That's the R. That's the magnitude of where we've gotten to. But what we have to do here is look at the summation of these two forces, right? So if I were to express this, all right, if I were to express this thing as two vectors, what would the first vector be? Let's put it in polar form. Let's deal with polar form just like we've been doing up to this point. What would the first vector be? 43, the speed is translates into what? This is the magnitude, right? So it would be 43 times cosine of 35 degrees plus I sine of 35 degrees. And then we're going to add that to what? That's the first 4 hours. We gotta do something here.
Wait, wasn't it the first
3 hours. So we did that for 3 hours.
And then you did the other one for 4.
We do the other one for 4 hours. Same speed, because they didn't tell us. Okay, and cosine of 120 plus I sine of 120 degrees. So that's the two quantities that we're dealing with here. All right, now let's get this stuff out of the way so we can see this. What we're trying to do is add these two things together. Now, did we, in any of our polar form operations, complex number operations, did we do any addition of these things? We never added polar form, did we? But we did add
Standard.
standard form. So what do you think we need to do to make this addition work?
Change it to standard.
Change it to standard form. So if we take the first vector, and the reason that I multiplied by 3 here is that this represents the distance covered in 1 hour, the magnitude of that thing. So what would the standard form of that one be? 3 times 43 is 129 times, what's the cosine of 35 degrees? 0.82. Give me another decimal place.
819.
819. Let's do that. Let's go 3 decimal places because we want to be as accurate as possible. Okay, and then the next one would be I sine of 120, or excuse me, sine of 35 degrees is 0.574. Okay, and we're adding that to 4 times 43 is 169 times cosine of 120 degrees, negative 1/2, and I times the sine, let's see, sine of 120 degrees is square root of 3 over 2, which is what, 0.7 something? 0.866. It doesn't matter. The i's fixed to disappear. I mean, we're just doing this kind of whole form. Now, do this. This times this, plus this times this. What's that going to give us for our real component? Yeah. Well, I mean, it's going to be a negative 1/2, so you'll end up subtracting. But in your calculator, 129 times 0.819 plus 169 times negative 0.5. What do you get? 21.51. Okay. And then do this times this. 151. Then do this times this plus this times that. 129 times 0.574 plus 1. That's 169 is wrong, guys. How'd y'all let me do that?
I don't know.
We got to start over.
Listen to you.
It's 172.
172. Yeah.
I wrote in pen.
Just scratch it through. Sorry.
Now it's 19.651.
19.651. Yeah, you could just go second enter and pull that old thing back up and just change 169 to 172. And what do we get for the second one?
222.998.
Will that turn to negative since it's the last?
No.
It's
It was
us.
99.
I would cry. Honestly.
Okay. Now, that is the result of these two forces acting together. Now, let me ask you this question. What is the magnitude of that force? Or what is the magnitude of this thing?
Oh, you square root.
Square root? Yes. So see, we're still doing it. Nothing new here. I just had to tell you what to do to get started. So the magnitude of this thing is going to be the square root of 19.651 squared plus 222.998 squared, the square root of all of that. 220, 223 point, let's call that 9. And that is what? That's the knots. That's the distance, right? That's the distance from the starting point. Because it traveled at one distance at 35 degrees, and then it switched directions and went 120 degrees, and then this is where it ended up, 223.9. Okay? The radius, the absolute value of this thing is the, let me kind of show you what it would be.
Not the square root of it.
It's the square root of this thing squared plus this thing squared without the
My
I.
calculator doesn't do that.
You got to use parentheses. It
I
does do
did.
it.
It like the
Yeah,
square root bar didn't go all the way over.
gotcha. Now, what's the heading here? From
84.96.
how'd you find that?
I just did 10.
Inverse tangent of 222.998 over 19.651 is our theta heading. So we're 223.9 nautical miles away
What?
What is this?
at an angle of
84.96.
84.96 degrees.
What did you do?
10 inverse.
B over A, right?
Yes.
What?
Yeah. All right, so now this is where we're headed with this, and this is kind of the stuff that we're going to be fine-tuning and honing over the next few days, putting these concepts into practice. Now, you probably will not find a lot of textbooks that take this approach to this. This is kind of my approach to it, but this is where we're going. Now, let's clear this because I want you guys to, let's look at the picture, and maybe this is something we should have started with. We have a ship leaving from here, right? It travels at 35 degrees for 3 hours, and then it turns and travels at 120 degrees for 4 hours. And that's where it ends up, right there. Okay? Now, that makes sense that we have that. Now, there's another approach to this, a complete different approach, where you just say this is 3 hours at 43 knots. That's 100, no, excuse me. Yeah, 3 hours at 43 knots is 129 knots, nautical miles. And this one was 172 nautical miles. And then you can, I don't know why I put squared there. And then you can use the angles, find this angle, and find this angle. And just solve the triangle, right? Using the law of sines or the law of cosines or whatever thing comes into play. And then you'd still have to find this angle in the heading. I just think that learning to think of these vectors in terms of polar forms, complex numbers, is the quickest way to deal with it. Right? So that's this is kind of an end result problem. These are the kinds of problems that you would see on the quiz. Okay? Along with some basic vector operations.
Wait, so what's basic?
Adding, subtracting vectors in component form, putting them into component form.
How do we do that?
That's what we're about to
that's what
cover.
we'll do that next.
All right? All right, so that's this. Oh, there, we got it right. 224.2 bearing 84.9 degrees. So we're good. I didn't practice this today, so this lesson's pretty cold. Here's what we're going to learn about today. Maybe not all these things. We're going to learn how to represent vectors as directed line segments, how to perform basic vector operations, multiplying vectors. We just did all this, and we just multiplied that vector by 3, right? Because it's 3 hours of that, 4 hours of the other thing. How to write vectors as a linear combination of unit vectors. We'll do that somewhat. We just did that as well, and we added the two standard forms together. How to find the direction angles of vectors. We just did that. The direction angle of that vector. How to use vectors to model and solve real-life problems, and why. Okay. Many real-life applications, such as calculating the effect of the wind on an airplane's path or currents on a ship's path, those types of things are really, really important to real life, so to speak. Okay? So we can see a vector as a directed line segment. And we've already been doing this, right? If we have the point AB in the XY plane, or that would be what in the complex plane? The point AB would be what in the complex plane?
No.
It would be A plus BI, right? A plus BI in the complex plane translates to, this is vector notation, okay? That's called component form of a vector. So anytime you see this AB, what that is defining is the vector that starts at the origin and ends at that point. Okay? Y'all all right with this?
Wait, so there's the ones with the little pointy ones, and then there's one with parentheses?
Yes, this is just a coordinate.
Okay.
Okay.
So,
This is what we would call coordinate form. This is complex form. This is component form of a vector. There's one new thing on the board, and that's the component form of the vector.
and the component form you said was?
It's just the same as the coordinate form, except we use these
Okay.
pointy things instead of parentheses.
What are those things called?
I have no idea.
I bet they don't have a name.
No. I'm sure it does, but I don't know it.
Oh, the little pointy bracket thing?
Yes.
Yeah, I don't know.
So you found something that I don't
We
know.
didn't use those.
But none of you know it either, so there you go.
I don't think we used
All right.
those.
You may not have. All right, now listen. How would we find the magnitude of this vector? It's equal to, the magnitude of this vector is equal to, we've already done it,
Square root of A
square root of a squared plus b squared. Yes, it's not new, right? It's the same as finding the absolute value of the complex number. How would we find the heading, the direction of it? The angle. This angle theta is equal to the inverse tangent of b over a, and of course we got to place that thing in the right quadrant. So there's always that disclaimer. We got to make sure we get the reference angle into the correct quadrant. Okay? So the only thing new so far is, hey, this is another way we can write a vector. All right? That just means a vector that ends there. It still has a radius value, a magnitude, an absolute value, and it still has a heading, and it's the same as what we've been doing. Okay? Now, moving forward, let's look at a two-dimensional vector. This is just kind of some words that represent what we just did. A two-dimensional vector, V, and the reason we're talking about two-dimensional vectors is because there is such a thing as three-dimensional vectors. It's an ordered pair of real numbers denoted in component form. This is called component form of a vector. Anytime you see these angular parentheses, I don't know what else to call them. The numbers A and B are the components of the vector. The standard representation of AB is the arrow from the origin to this coordinate. All right, so that's the relationship in that. The magnitude of V is the length of the arrow, and the direction of V is the direction in which the arrow pointing. All right, and we just discussed how to find the magnitude of V. And the vector 0 is just called the zero vector. If you see 0 represented as a vector, that's 0, 0, right, in the coordinate plane. 0 plus 0i in the complex plane. That's the complex 0. Right? Okay? I want y'all to see the correlation between this and the complex plane and how we can use complex polar form to do vector operations. Okay? Now, we've got this. Initial point R, terminal point S, and an equivalent vector over there, P. Now, how would you show that these two vectors are equivalent? What would it mean for vectors to be equivalent? Equivalent vectors would have to have the same what and same what? Same magnitude and same direction. Right? Are they headed the same direction? Do they have the same magnitude? How would we figure that out? Yeah, we could solve each one of them. I'm going to show you some simple ways to do this, but to solve this vector, we would need its direction and magnitude, right? And to solve this one, we're going to need its direction and magnitude. So I need A and B values on these two things. And I'm going to see really quickly that they're the same. What is the distance right here from this point to this point? 3 is the distance, right? And then up we would have from 2 to 6, that's 4, which means the magnitude is 5. Look what we have over here. 3, 4, 5. So are they equivalent vectors? They absolutely are equivalent vectors. All right? Now, one of these vectors is in what we call standard position. The other is not. Standard position, it's at home. It's at 0, 0 is where its tail is, and then its tip is at 3, 4. Okay, so how would you translate this vector or show that this vector is the same with that kind of thinking? What would we have to do to point R to make it 0, 0? What would we have to do? We'd have to move it right 4 and down 2. What if we move this point right 4 and down 2? What do we get? What's negative 1 plus 4? 3. What's 6 minus 2? 4. Okay? So if we need to translate a vector to standard position or translate it to the origin, we're just going to do whatever it takes to move that vector over. Okay? Now, are y'all okay with that? I know we're kind of just covering some random things. The great thing about vectors is that the hard work is already done. We've already done the difficult work understanding these angles, understanding how to find magnitude, understanding how these things relate to each other and interact with each other. Vectors just comes, we're putting some really easy concepts together into kind of a culmination of things. If V is represented by an arrow from x1, y1 to x2, y2, this is what we just looked at, right? Yes, 2 points, a vector between 2 points.
Wait, why is there 2 absolute value things? Is that what that is?
Yes.
Why?
It's to signify that it's a vector.
Okay.
Okay? And it's actually magnitude. Anytime you see this with 2 bars, it's a great question. Anytime you see this with 2 bars, what we're asking for here is the magnitude or the norm of the vector V.
So norm means magnitude
Yes.
in vector language?
Yes.
Is it only in vector language?
No, it means magnitude in mathematics everywhere. So anytime you see the norm of something, that's the absolute value of it.
Why do they have multiple ways to represent it?
It's just kind of standardized if you're dealing with vectors to write it that way. Okay? They're asking you for the magnitude of the vector. And if V is equal to component form AB, that means it's in standard position, right? Standard position 0, 0 to point AB, then it's just A squared plus B squared square root of it. All that's new. And what is this first thing, guys? What is this formula right here? Doesn't that look familiar? That's the distance formula. It's the distance between the 2 points. I mean, again, nothing new. The only thing that's new here is this notation. This means the norm of V or the absolute value of V.
This is a lot to take in.
But it's not new. It's just new notation for the same old things. This vector, for example, Emma, what we're talking about, when we're talking about this vector is from the point 0, 0 to the point A, B. Yeah. That's what component form is. And we know from lots of practice up to this point that the
So it always
norm of
starts
that
at
thing
0,
is
0?
there. Yeah,
If it's in component?
that's right.
Okay.
If it's in component form. Now, this says find the magnitude of V represented by PQ, where P is 3, negative 4, and actually we need to, I don't like this symbol here. The vector symbol is going to have a little arrow up like that. It's just a little half arrow, like.
Half arrow, okay. But since it's that, it's
Okay.
hard to tell.
Find the magnitude of that vector from P to Q, where P is 3, -4, and Q is equal to 5, 2. Now, would we, how could we do this?
Square root x2 minus.
Yeah, we could use the distance formula, and we could say the distance here is equal to the square root of 5 minus 3 squared plus 2 minus -4 squared. And that's equal to 4 plus 6 squared, square root of 38, square root of 40, square root of 40, which we would simplify, or could simplify, to be 2 times the square root of 10. How else could we do it? How would we translate this to the origin and put it in component form? This is some of your problems. We're just going to ask you to write the component form of the vector. Component form would be the equivalent vector to this that starts, instead of at 3, -4, where does it have to start? It starts at 0, 0. So how would we translate it to 3 negative? How would we translate 3, -4 to 0, 0?
Negative.
Subtract 3 from the x-coordinate and add 4 to the y-coordinate. That would be subtracting 3 from this x-coordinate and adding 4 to that y-coordinate. What's 5 minus 3?
2.
So PQ is equal to 2, 6 in component form. And then the norm of PQ is square root of 2 squared plus 6 squared. Same thing, right?
Okay.
Now you decide which one is easier. I like this way better.
That sounds nice to me.
You know, because we need to always be able to translate vectors to standard position or to the origin. And if we're translating this to the origin to put it in component form, we do this. And then if I had any operations that I wanted to do with it, I just use the rectangular form of it anyway, right? Rectangular form, this vector is 2, 6. Component form, 2 plus 6i, complex form. You can find the angle, square root of 40 times cosine of whatever the angle is, plus I sine of the angle, and do whatever I needed to do with it. All right? Let's go to another example here. Vector addition and scalar multiplication. We're almost done. We're almost out of time. We got 3 minutes, don't we?
We have like we have like no time.
Yeah.
Okay.
Do we have homework?
Yeah, let's look at this real quickly. It happens exactly the way you would want to. Give me 1 minute. I'm going to give you this. We're given 2 vectors here. Find, this is u and this is v. This says find 3 times u plus v. How would you do that?
Make it standard.
3 times u equals what? 6, -3. Plus, and v is just 5, 3. So if I add these 2 together, what do I have? 11, 0.
So you don't change anything back to
No.
the origin or anything like that?
No. Now you could, if you wanted to, you could put this in complex form and add it, but it just works exactly the way you think it should work. All right? Sorry, I'm keeping you guys a little bit late. The practice problems are those problems right up top. This is quite a few problems, but they're pretty quick. It shouldn't take you very long.